Atomos, or not to be cut in Greek. This is a look at the history of the development of atomic theory. This atomic model may look pretty familiar to you. It's what we call the Bohr model of the atom. It's a model. You got to remember that a model uses familiar ideas to explain unfamiliar facts. And models change as new information is collected, and that's what this podcast is about. Well, who are these guys? Whole bunch of men. In this podcast, you'll learn about them and the quest for knowledge about the fundamental nature of the universe and how what they did helped define our views. The atomic model has changed, starting in about 400 BC when it looked like a billiard ball. You see, this is the Greek philosopher Democritus, who began the search for a description of matter more than 2,400 years ago. His basic question was, well, gee, if you cut matter in half and then in half and then in half and then half, will it go on forever, or was there a limit? There are stories of him walking on the sand on a beach, thinking about stones becoming pebbles, becoming sand. I think you get it. Well, he decided that there would be a smallest possible piece of matter. That piece would be indivisible, or not able to be cut, and he named it atomos. To Democritus, atoms were small hard particles that were made of the same material, but they were different in shapes and in sizes, and, well, atoms were infinite in many ways. They could move, they could join together, but there were atoms of just about everything. And this theory was ignored and forgotten for many years. Why? Well, the guys in charge, the eminent philosophers of the time, Aristotle and Plato, had a more respected and ultimately wrong theory. They had 4 elements: earth, air, fire, and water. Well, their ideas held sway because of their eminence as philosophers, and the atomos idea was buried for many years. Here's sort of a timeline. 400 BC, we have Democritus. Then we have Aristotle's 4 elements for some 2,000 plus years, and then we have John Dalton and his model in 1803. Dalton used the work of Antoine Lavoisier and others, and he performed several experiments himself, and eventually it led to the acceptance of his idea of atoms and Dalton's atomic theory. He deduced that elements are composed of atoms, that atoms are indivisible and indestructible. Atoms of the same element are exactly alike. Atoms of different elements are different. And the key thing is that compounds are formed by the joining of 2 or more elements in chemical compounds. So we had basic building blocks called elements that came together to form compounds in chemical reactions. This theory became, and it still is, one of the foundations of modern chemistry. Well, about 90 years later, the English scientist J.J. Thomson provided the first hint that, in fact, atoms might be even made of smaller particles, that they weren't indivisible. He studied the passage of an electric current through a gas, and, well, as the current passed through the gas, and it didn't matter which gas it was, it gave off rays of negatively charged particles. He proposed a model of the atom that's sometimes called the plum pudding model. I like to call it the chocolate chip cookie dough model since plum puddings aren't very common these days. He basically said that atoms were made from a positively charged substance, that would be the cookie dough, and it had negatively charged electrons, those would be the chocolate chips, scattered throughout it, he said, like plums in a pudding. This surprised Thomson because, well, gee, where did the negative charges come from? After all, the gas atoms were uncharged, so he was puzzled. He concluded that the negative charges must come from within the atom, that a particle smaller than an atom had to exist, that indeed the atom was divisible. He called the negatively charged particles corpuscles, although today they are known as electrons. Well, since the gas was known to be neutral, having no charge, he reasoned that there must be positively charged particles in the atom, but Thomson could never find them. However, by examining the backside of the apparatus used by Thomson, Eugen Goldstein discovered the proton. But because of differing opinions of his colleagues, he was, and he still is, widely ignored, although you can find references to his experiments and his publishing about the proton. Moving along. In 1908, the New Zealand physicist Ernest Rutherford was working on an experiment that, seemed to have little to do with unraveling the mysteries of atomic structure. His experiment involved firing a stream of positively charged alpha particles in a very thin sheet of gold foil. Gold can be hammered into a foil of fewer than 2,000 atoms thick.
Based on Thomson's model, Rutherford expected that the positively charged alpha particles should pass through the uniform sphere of positively charged matter with little or no deflection. Click on Actual Experimental Results to see what actually happens. Rutherford observed that the majority of alpha particles penetrated the foil either undeflected or with only a slight deflection. Every now and then, however, an alpha particle was scattered or deflected at a large angle. In some instances, an alpha particle actually bounced back in the direction from which it had come. This was a most surprising finding, for in Thomson's model, the positive charge of the atom was so diffuse or spread out that the positive alpha particles were expected to pass through the foil with very little deflection. Upon making this discovery, Rutherford exclaimed, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Click on Rutherford's model to see the model of the atom that Rutherford proposed based on his experimental observations. Based on the results of his experiment, Rutherford postulated a nuclear atom. All of the positive charge and most of the mass of the atom is concentrated in a very small volume called the nucleus. Electrons occupy the remaining space of the atom. The radius of an atom is approximately 20,000 times larger than the radius of the nucleus. Most of the positively charged alpha particles pass straight through the diffuse electron clouds of the atoms. Some alpha particles pass close to the small positive nuclei and are deflected at large angles. A few particles score a direct hit on the nuclei and come almost straight back.
So this was Rutherford's explanation of the diffraction patterns that he saw of the alpha particles. This could only mean that the gold atoms in the sheet were, mostly empty space. Atoms weren't a plum pudding filled with positively charged material. He concluded that there was a nucleus, and that the nucleus must be positively charged since it repelled the positively charged alpha particles. He called the center of the atom the nucleus. Shortly after, in 1913, the Danish scientist Niels Bohr, working with spectra of hydrogen, proposed an improvement. In his model, he placed each electron in a specific energy level, and this has led to the Bohr model of the atom, one that you're probably familiar with, where electrons move in definite orbits around the nucleus, much like planets around the sun. This is in fact called a satellite model of the atom. And these orbits are specific distances from the nucleus, and we sometimes call them energy levels or shells. Well, turns out that Bohr's model didn't work well for any atom but hydrogen, so it too has been modified. And today's atomic model is based upon the principle of wave mechanics. According to the theory of wave mechanics, electrons don't move about an atom in a definite path, like planets around the sun. Indeed, their path is really of little interest to a chemist these days, because it's impossible to determine where an electron is. We can find out where it probably will be, and that is based upon the energy state of the electron. We will spend a lot more time on this in a couple of months. So for now, let's just end with, according to the modern atomic model, the atom has a small, positively charged nucleus which contains the protons and the neutrons, and it is surrounded by a large region in which there are enough electrons to make the atom neutral. And so if you compare the models, you'll see the natural development to the wave model of the atom at the bottom, where there is a nucleus and there is an electron cloud. And that's really all we need to know for now.